last time we talked about it. Now we define these based on a set of Cartesian coordinate. If space allowed you to do that, that is more convenient. So we have a set of Cartesian coordinate, x, I, and then we have basis, Cartesian univector basis. Right. And we want to transform it to a set of coordinate which is non-Cartesian and non-linear, generally non-linear. So q's of I, which can be a function of x, right? And then we define the basis for this set of coordinates, called the epsilon. We define the covariant basis first. Basically, it's defined as partial x, partial I, right? And which is just, you substitute this into that, which is just partial x. Actually, x, because we substitute, we need to change. And then which is like transforming the covariant vector, covariant using the transformation group or covariant index. We use this rule. So, and then with that we can transform a little differential of the spatial vector, because we cannot transform it globally. These q's are nonlinear. We cannot don't make the error that write like q. We cannot do that. Right? This is not correct. Right? You cannot transform like this. Is this transformation is nonlinear. So this transformation matrix is not a constant. It's a function of space. Okay. So this, you can only transform it locally, transform a little bit of displacement, a little change in the displacement. Right? So this is ordinary in the Cartesian coordinate is this one, right? Right? And now you transform to the new coordinate system, I, right? And this dqi is just transform according to the contravariant index. So it's actually no, x is dx. This is transforming the change of the position, right? And so with that we can define the ds square, which is like the norm of the displacement change. I mean a little differential dx. So in Cartesian, obviously is trivial. It's just some of I squared, di dxi squared, right? And now for the new coordinate system, what we have is gij dqi equal to, and for Cartesian, obviously, you just sum over three terms. So you have dx1 squared plus dx2 squared, dx3 squared. But this one has all the possibility, all 9 elements, right? Because this is I is going from 1 to 3, so this is a matrix of 3 by 3 matrix. You sum over all if all elements are not 0, then altogether there should be a 9 term. But there's a symmetric property of this G because you substitute this into here, So dx squared, this is this the square of that. You see that Gij, what we call the covariant metric tensor, is defined as this epsilon I dot epsilon j. And they are, obviously in symmetric because you plug in this into here, it becomes dx k plus q. Right. So, right, you see that there's symmetric. You can, because now after you write in this form, the order doesn't matter. You can interchange the two. So yeah, this is just after take a derivative. These are just number. You can interchange the position. So Gij is equals to Gji. So the metric tensor is symmetric. Okay. Now I think last time we stop it here. And I think your textbook later immediately defined the contravariant metric tensor. And you can do that, but we could actually do the other order. Go to the a little bit later in the section about the using the contravariant basis, right? And, so we could start from here and define the change in the dx. This dx, you can also writing it in contravariant basis. So basically, you change this to dqi. Although this is not, I mean, you exactly what this is. It's not that important for now. You can figure out what this is later, right? And then the basis is with the superscript, right? And that superscript basis, the contravariant basis, you can define it just like how you transform a contravariant vector. Basically, that's like here. So basically, epsilon I with the superscript is defined as just the same. Positive qi xj and ej with this superscript univector in the Cartesian univector, but they are actually the same in Cartesian coordinates. Just wait. So ei is just the same as e. Right. So in Cartesian coordinate, it doesn't matter going up and down. So that's why it's a little bit redundant in defining the contravariant or covariant for Cartesian coordinates. But for general coordinate system, this is different. This superscript epsilon is generally different from this subscript epsilon. Okay, so it transforms differently. So what subscript is transformed like this, the superscript transformed like this. Okay, so that is all fine, and obviously the same as this dq. All right, it's just it's a covariant quantity, so the transformation is just like this one. So it's also xj across qi. This is subscript defined like that. Xj the superscript, and then dx dxj in the subscript now. But again, in the Cartesian coordinate, dxi is the same as dxi. So it doesn't matter. That is how you define this dqi. But The usual thing for now is this epsilon superscript, right? Because that will allow us to define a contravariant metric tensor. So similar to the covariant metric tensor, which is the dot product between the bases. In the superscript, now you can define as superscript dot. Okay, that is the definition. So again, after you substitute this into here, you can write it like partial I partial xj partial j partial xj sum over k, right? Because you substitute this into here, and you take a dot product, right, between the two, and get you have a conical delta to allow you become a sum over this k index. Okay, and again, you can see that they're symmetric. So this is okay. So now you define this contravariant metric tensor, and then you now look at the property of the relationship between these two. So the idea is you can write either one, or that doesn't matter. Gij and contract with this contravariant ones with one index, the jk, right? And what you have is the sum. Just put these substitutes and that into here. Okay, and then put that in here, except that this is jk instead of ij, and then so qj. Now we cannot use k, like and use L. This is jk, so k. Oh, we cannot use k. ij. We already use k. This g j. So I probably should not use k here. We already use L. Let's use m. I j j k. Okay. L. So this is jk. This is k, and this is the same. Right. So substitute this key definition into here, and now you can use the chain rule. Say group these two terms. This is like a chain rule and sum over j, right? So this becomes a delta, conical delta. This is conical delta m l. Right. And now you use this conical delta to sum, make another sum, right? And yeah, which one's solution? We can sum the L, either M and L, right? So although now the sum is we might need to explicit, right? This is not exactly according to the rule of the superscript and subscript sum, because this is coming from the transformation matrix, and you get the exception that you sum over the same subscript, and here sum over the superscript. This is superscript, this is subscript. No, this sum over this m. Oh, this becomes a partial xl qi and partial qk partial xl. Right now you sum over l, and you see that this is conical delta. This shows that the two metric tensor, the covariant and contravariant, they are inverse of each other. So you can say G, it's just inverse of G. If you call this G, the covariant is G matrix, then Gij inverse of Ig. That's not the notation. That's a little bit confusing, but you know what I'm saying is that originally we define a covariant metric tensor this way by using the covariant basis. Now we define another object, the contravariant metric tensor, using contravariant basis, and then we show that the two metric tensors are inverse of each other. Okay, so this is a property, and this is a little bit different from the order of the textbook. The textbook defines the contravariant one by this information, by this relationship. Just define a contravariant metric tensor as the inverse of the covariant metric tensor, which is fine. And then either way, then you can show that that object will satisfy all these when you define the contravariant basis. Okay, and so up to here. And I mean, it looks like a lot of definition, but both are important, both are useful, because one very commonly used is all these metric tensor is to use change the subscript and superscript. Yeah, sometimes use it to, because sometimes your indices are not in the right position, and you want to follow the rule that you sum over them, superscript and subscript, but they are not in the convenient way. Then you use the metric tensor to change it, like the subscript to superscript and superscript to subscript. And we'll see how you do that here. So first you notice the property of these two bases. You write the dot product, the subscript one, dot and the superscript one. And you see that by substitution of the definition, this one is x. We already used k, also qi, and then this is ek, and dot into this one, this definition, also qj, also x to l. This is in this, but they are actually the same. We actually we use the property that the Cartesian coordinate bases are the same. But this start into that, and also the conical delta, right? So k, you have a conical delta k and l, and then you can use that to either sum over l or sum over k, right? And then so that means this conical delta kl and sum over either one, so it becomes a partial. Yes, that's what it is. So okay, L and conical delta here. Right, and then use one of them, sum over, like say sum over L, then you can probably xk, qi, qj, xk. Now you sum over k. That is like a chain rule is qj is also conical delta. Okay, so these bases, they are orthogonal to and not orthogonal. They multiply to conical delta. It looks like this is not a matrix. This looks like it's a vector. They they kind of orthogonal because if I is not equal to C, they will be 0. But generally, they are not the same, unlike Cartesian univector. Okay, so that is the basis. Now you can use the property of the basis to do the lowering up or rising a little the index. I'm just looking for space. And I don't want which one is useful. See if I still have some space here. Just start writing from here. So if you have any vector, say any vector A that you want to write as any equals to AJ is okay. You can either write it in covariant basis or contravariant basis, right? And now the better way to look at this is because we want to change the like a contravariant one to a covariant one, right? We do that when you're looking for which relationship you should use. Yeah, maybe we can dot say just dot one with either one of the bases, like AI, dot into a contravariant basis. Right, that is AI. Dot into epsilon j. Right, and now you use this one. This is a conical delta ij. So this is a after sum of I, a superscript j, and this is our contravariant metric tensor. And the order doesn't matter. You can put this in the left or in the right because this is symmetric matrix. That doesn't matter. So you see that you multiply a covariant coordinate with a contravariant metric tensor, sum over one of the index. And what is left is the other index, and that becomes a superscript. This is a subscript, and you change it to a superscript, right? If you do it the other way around, instead of dot into, again, do exactly the same, dot into a AI epsilon and dot into epsilon j out of the frame. That like in here, this equals to here, you have AI subscript I dot into subscript j, and this is a conical delta. This becomes a j, and this is a covariant metric tensor, so AI d. Okay, so you multiply a contravariant coordinate with covariant metric tensor, you change it to a covariant coordinate. Okay, and that works for all indices. So if you have a tensor instead of vector, you want to change one of the index of the tensor from superscript to subscript, then you multiply by a covariant metric tensor. And then you do exactly the same contraction and change it from a superscript or subscript, a subscript to superscript. So using this kind of a multiplication. It's okay. So and that is very convenient in doing all these tensor things, and we actually will do that, use that in some of the discussions right away. And I think that's covered the next part of the textbook. So I think I covered all the equations from 4.44 to 47. I covered everything. Okay, so it's okay. All these this is somewhat abstract. So just define something that will be useful. And if you want to make it a slightly less abstract, you can do the example like these are any arbitrary coordinate. You can now say you choose it like your spherical coordinate or your cylindrical coordinate, and work out these or this Gij for or the epsilon for the coordinate system and all the Gij and all that, and make it slightly more general. You can use the language in the what we call the curvilinear coordinate system. In chapter 3, we have a section about that. Section 3.10, and those are for coordinate system that is also generally nonlinear, but it has the property that the coordinate coordinate vector, if you use this language of this epsilon, they are actually orthogonal to each other. So all these right here, you define like that, all these epsilon I from 1 to 3, they are not necessarily orthogonal to each other. So they can have they can have off diagonal terms. Therefore, this epsilon, this Gij can have off diagonal elements. But for curvilinear coordinate, then the off diagonal elements are 0 because they are perpendicular to each other. So only the diagonal line, the metric tensor, only the diagonal has non-zero element. Okay, your question? Which line? This line? This no, I said this is not correct. You maybe coming in a little late, but I'm writing is this is the position vector in Cartesian coordinate. You can write like that. But after you transform to general coordinate, these Q, all these Q superscript 1 to 3, your choice of coordinate, and generally you cannot write it like that. Right? You cannot write the coordinate times the basis vector in here to express x. Right? This is, I think I graphically explained that to you one time or last time. Okay, because this transformation depends on position. They are nonlinear, so you cannot transform the whole vector from the same way, just using the same transformation matrix. So you cannot do that. You can only just transform the variation of the position vector. So this you can only transform dx, right? Right. So you write like that, the generally is incorrect equation. Therefore, I write cos here. This is not a correct equation. It's okay. You don't make the error. Don't make this one. It's okay. Then you want to go through that quickly. So Cartesian coordinate, just follow all the rule. So we can erase up to here. These are just the discussion of the metric tensor. Okay. Now your particular choice of qi in this is spherical coordinate. So all. So q superscript 1 is all, and then 2 is theta. Right. Obviously, you need to define your transformation, how you transform from x, y, z to this r theta phi, which you should, supposedly you know, that's like x, y, z axis, and r at a location r. This is theta projecting on xy plane. This is phi. So obviously, x is r project on xy plane. Right. This then project on that and project on the x-axis. R is sine theta cosine phi. X is r sine theta cosine. Right. And likewise, it's r sine theta cosine phi, and z is r sine theta. So this allows you to do the differentiation. So partial. So all this differentiation, you can do that. So this is like partial 1, partial x superscript 1 is partial x. Let's say 1 is partial x partial r. Partial x partial r would be the sine theta cosine theta. Okay. Likewise, all these 9 elements, you can do that, right? So that's fine. So once you do that, you can work on your G major, which probably erase that. But anyway, that is fine. And then obviously you want to transform it the other way around. You need also this matrix, and so then you need to get the inverse relationship, inverse relation. So therefore, like R is easy. It's just x squared plus y squared plus c squared. Theta is like here, so it's the arctangent of well, this is C, projection is C, or C of, I mean, you can use arc cosine or arc cosine Z of R, right? Z of R, well, C R is there's sometimes working on the arc the inverse trigonometric function can be a little tricky. This becomes a multi-valent function, so you need to be very careful. And then phi is obviously also phi is arctangent. This is minus x arctangent y. Right. And the idea is that when you take partial derivative, you keep one set of coordinates fixed, and then express the in terms of the other coordinates. So you take the like this matrix. You like partial r, partial x. You use this and do a partial derivative with respect to x. And likewise, all these elements you calculate that way. This usual partial derivative. And when you do the partial derivative, you don't want to mix your coordinates. Say you express everything to a new coordinate system in terms of old coordinate system, which are Cartesian. And after that, you do your partial derivative. You mix, so you sum of it on the right hand side involving a new coordinate system, and you do a partial derivative, that you can make error that way. You just need to be a little careful. All right, so that's how you calculate this transformation matrix, and then you can define all that. And for example, you can, after you do the transform, the derivative of that, you can calculate explicitly what these epsilon are, right? Like I think those are straightforward. I don't need me to go through it. So your textbook has that, and the team the Gij is also once you figure out all this epsilon, Gij is once you get the exact form, just do the dot product. And you convince yourself that off diagonal elements are all zero because this is a Cavalier coordinate. So all the off diagonal terms are zero. And also, now you do the inverse, then you can define this this contravariant basis also, and then calculate the contravariant metric tensor about this dot product. That also should be straightforward. Okay. After this example, I think all these, I think I cover some of this also. The dot product between tensor, between vector is this. Now you have a different way of expressing that. So, well, already writing it like that, you can have two ways of expressing a vector. So let's just erase all this sample. Straightforward, and then you can look at the textbook and figure out. So the dot product between vector, you can have different way of writing it. If you have one is in contravariant coordinate, and the other is in covariant coordinate, then you use this relationship. That becomes a conical delta, and that. Right, so that is one possibility. Now you can also use this lowering and the rising or lowering operation to write it either like if you change that multiplied by a contravariant. You write it like so AI with this. This is a subscript, right? Subscript you can write like a superscript A G L J. No, wait, this subscript J I. Right, J I. Okay. Right. This is you write like this is the IJ. I mean, you can interchange the order, doesn't matter. Not IG. Right. So that product also can be expressed like that, and you can also convince yourself that also can be written like that. Okay, so there are at least three ways you can calculate your dot product between vector, and likewise all the contraction between tensor and vector. Do it in multiple ways.